Hey, good morning, everyone. So my name is Zhou, and so focus modeling is part of CGI interaction modeling, and focusing on that's the dark hole before one goes to science observation. And we strive to provide the credible low contrast prediction for the as-built chronograph system, whether it's the testbed, CGI ground, or future IC. And with the credibility as the basis, we to provide system management for engineering decision making, risk assessment throughout the CGI cycle. And as part of our model, we use the same CGI control model, focus control model, algorithm, the procedure, the regularization strategy, and constraint, and so on. As for the model itself for the TVAC, it is largely the same as what we have updated. And there are some modifications done. So those are yellow highlight text. So I'm only going to stress a few points here. So the input to model are mostly measurement based, which includes all the usual stuff listed in the box here. And there's one notable addition. That's the phase retrieval as measured. This is to imitate the post-branding with an error. And for the result I'm going to show, I also use no additional uncertainty items. This is just for figure fun time. On the control model side, we also use this retrieval as measured correctly instead of using the calculated EPU from the choose model. The waveform sensing control model, we use, as mentioned earlier, we use this standard pairwise probing and the EPU conjugation just as incremental CGI, which Eric covered yesterday very well. So I'm only going to just stress one point that for models, since we don't have testbed, we rely on the choose model and also use the as-built detect model as described to generate the images over the finite bandwidth. And that's just the main modification. It's the debug configuration. So this is the result of our model validation in the TVAC on the raw context. So this is a big opportunity for us to validate our Hopeless model against the CGI instrument. Honestly, I was a little bit nervous because I don't know, after 5 years lack of anything, know if all the pieces will fall in together or not. But turns out it's surprisingly well. So as the two plots here show, our as-built pretest prediction of the raw coherent contrast agrees very well with the TVAC result. The prediction error is less than 25%. And also the total number of iterations are in the same ballpark of few tens instead of hundreds as used to be on the testbed. And this is the first time we got this much close in terms of number of iterations. This is also indication of future timing budget for the IOs. So part of the reason is the team managed to successfully apply the HSC design DM solution to start the Hopeless sequence. And you may notice a little bit data in sync between these two curves, the model versus the TVAC, and as well as the converging speed, not as similar during the first stage of iteration. And this is because the model was run before the TVAC test, but during TVAC, the team had to adjust. They want to adjust on the fly by the need or perceived need and preference. There's also some other difference between model and TVAC as far as like the lot of tuning parameters, or the usage of the EMCCD operating parameter, those kinds of things. So there's still slight difference, but as a whole, we think this is a very good agreement as a whole. And I also want to point out that our model also makes a lot of recommendation during the TVAC, and which greatly helped the TVAC office execution to success, especially the very first one. This one is the second. I also put second kind model validation here, which is uncertainty-based Monte Carlo prediction without any flight calibration data. So in this case, the TVAC raw contrast is right at the predict maximum. This is not fantastic, but considering the circumstance that we had quite some unexpected over the requirement imperfection related to the DM. So this still is a good data point, maybe for the future HWO. Yeah, I'm looking at the caliber. It's not caliber's fault, but certainly is DM related things that's beyond our control. This table just puts the few numbers together on the TVAC measured. This is a coherent part. TVAC measured is just below 1.8, and our prediction of S-build as well as the couple number from the Monte Carlo prediction. In addition to the raw contrast, we have also some limited sensitivity, sensitivity validation data here. So the plot here left shows the model versus the measured. The dark dot and line are from the measurement at the June yesterday mentioned in his slide on the test number 3 with Zernike internal step input test. I believe he didn't put out the data or plot, yeah, but I saw his result. So we had in general have very good model versus the measurement agreement. Maybe perhaps the exception is Zernike 5, yeah. On the right table is the prediction error against the measurement, and you can see except the Day5 that's a little bit over factor of 2, but all the rest are very decent, and the mean is like 23 or 28% ish. Oh, by the way, we also had a separate Z2 and Z2, Z3, Z4 sensitivity test data taken, but unfortunately at this time we haven't actually analyzed it yet. Okay, switching gear. This is an example to show the Hoffice modeling also provides system engineering support. In this case, is the TVAC anomaly verification. And toward the end of the TVAC, we discovered an anomaly And the team initially first saw incoherent light here. Okay, this part here, in some of the barcode subband image. And later also some recent feature part probably already seen in yesterday Gary's presentation here. So there was some preliminary analysis done by Brian and Gary, and it points to the field stop diffraction from out of band spectrum through the gap around the CFAM. So the modeling team was asked to confirm the phenomena and assess the impact in orbit and the effectiveness of any potential mitigation, and also as an exercise as model verification. So based on the best geometry of the CFAM gap illustrated here, we run the beam propagation twice and then add them incoherently. So that is the beam propagates with wavelengths within the CFAM band pass through the nominal CFAM aperture, and then a second propagation of the wavelengths outside the CFAM bandwidth pass through the gap. And here is the result of comparing model versus measured. Top row is the measured pure image with field stop and the dark hole solution for subband A, 1A, 1B, and 1C. And bottom row shows the model of the same 1A, 1B, 1C. So you can see our model reproduce the pure image quite well with similar features, as well as the relative strength between the leakage, the preset feature, and the nominal signal as observed. Although in model case, we notice all the present is a little bit longer than measured. And this is another model versus measurement comparison. In this case, we compare both model and the measurement compare examines the bandwidth, the broadband, the source bandwidth impact. So on the leftmost is the full barrier spectrum showing on the right plot. So you notice the presenter feature is the most strongest, and in the middle column is in band about 10 or 25 millimeter nanometer in band. And in this case, you hardly notice because it's mismatched. So you hardly have the present feature observed. And on the rightmost column is, I'm sorry, I probably misstate. On the rightmost column is out of band. And then you see, you notice the feature in both measurement and model. So all in all, the model again reproduce the pure images as observed with the similar features. And both model and the measurement suggest that the leakage does come from the out of band diffraction through the CFAM field gap. This is the dark hole image model versus measurement. The middle two row model is the CBS and the one that's the closest. On the left is the measure, and on the rightmost is also measured, but subtract in band from the full band. So you see the leakage, the incoherent leakage part. So both model and the measurement are consistent in terms of contribution of incoherent due to this CFAM. We believe the contribution of from this CFAM is less than 10% for the TVAC completion. Okay, so this is another slide. This shows two things. First is the impact with in-orbit stellar spectrum. On the leftmost is the TVAC we just modeled, TVAC source, and the middle two are the two stellar spectrum B3b and G5b. And you can see without FAFO, the auto prediction says we'll have at least like 110⁻⁶. On the fourth column is if we install the FAFO with 7.5 millimeter diameter, then the impact is almost even level. Okay, so in summary, we had our opportunity to validate our Hopus model performance against the CGI instruments. We had a good result, agreement with the actual TVAC performance, and extending our success track record on model validation of S-built chronograph system in terms of raw contrast, contrast convergence, and some key sensitivity. And our uncertainty-based Monte Carlo prediction also goes with the actual TVAC performance. So it's it should be a useful data point for the HW case. And finally, yeah, our model verified a major TVAC performance anomaly for the case of CFM straight line. I think I'll stop here and just see if there's any question.
Discrepancy, like how much between the full truth model and the compact model, like what's the contrast difference?
We don't compare full model versus compact model, but I do have slide compare by model versus TVAC. I think I have.
Yeah.
So this actually is more about the incoherent light, but you can see I put here the table, the total contrast, the coherent part and the incoherent part. So the coherent part agrees very well, but the incoherent part, the TVAC is much higher. So that means the total contrast is like 3 or maybe close to 4 times higher. So yeah, that's a good point too. The model validation, the scope of model validation is always just coherent part. But this total or incoherent is always, I mean, especially after TVAC, it is a concern for us. And that's why in previous years, we want to make sure our total is below the coherent requirement. Yeah, that's the